We are also collecting those images. I have two groups. One group has already collected many images, so that they will be doing lab today evening.
Okay.
About the lab 2, and another one we have to wait probably 1 more week.
Yeah.
So that the enough collection. Did you say that like 5 to 6 images will be?
Yep. For lab 3, 5 to 6 is the bare minimum. If you have more, the better, because makes it easier to see the pattern. But if you think about it, it's a 4-parameter model. You got the semi-major axis, the period, the phase, and the tilt. So in theory, you could do it with 4 data points, but you at least want 1 for a check. And ideally, you have more than that, so they can really see the pattern. Double is best. Yeah, so like 10 would be nice.
Yes, I can still keep 1 more week, so that they will be go on collecting the images, and whatever comes until the next week, maybe 9, 10 images, and then work with that. That is my plan.
And it's also trickier this semester since we don't have Tololo. You're piecing it together from all the other telescopes. Where at Tololo, it's clear every night, except during our summer, their winter. They have 300 good nights a year. The 65 bad nights are all during our summer, when we're not really teaching students anyway, usually. So having Tololo, if you're observing for 2 weeks, you'll probably get all 14 images. But since we have to play this game, we did get an update. They said they asked for each team to send one person, have one person send an email, and they'll work with them. And they said, okay, you're good to go. You're back online. But there was almost no bandwidth, and then it dropped to 0 bandwidth. We've been sending an email every day saying, hey, we have no bandwidth. No response yet. So yeah, Tololo's not back online. But once it is, then it's really easy to collect that moon data.
But still, I had set 3 weeks back, and I have 14 images.
Okay. Great.
Yeah.
Great. That's the great thing of a global network. There's some telescope somewhere that should be able to do the job. They're not all uniformly high quality, but anyway. Hi, everyone. Good to see y'all. Any questions, issues, anything anyone wants to bring up before we dive in to Lab 4?
Yeah, so the lab 4, the asteroid observations.
Yeah.
I guess you were talking about Tololo not being effectively not there, right?
Yeah. So
should we just use the package stuff?
Yeah, you can use the sample data. It's unfortunate, but you're coming in. We've been running from Tololo since 2004. This has never happened. So this is not usual. You're coming in right now, and I don't want you to think this is typical. It's not typical. Even during the pandemic, Tololo was open to some degree. We kept losing telescopes because as telescopes failed, they weren't providing maintenance. But yeah, it's just very unfortunate situation with the cyber attack.
So yeah, which is fine. I went through the process with the students, even though I couldn't schedule it, right? So where is the did I miss that, where the data is stored, or
it's
the images?
In Afterglow, and I'll show you. I'll show you today. Okay. I'll show you where the sample data is, but then I'll bring up data I collected last fall, because the sample data, well, if you're collecting your own data, there's an extra step. Remember, we took a rapid fire sequence of 10 images from both sites, just in case they didn't start at exactly the same time, and if there are other issues. And so you have to go through those and find 2 that happened as close together in time as possible. In the sample directory, we've already done that. It's just 1 image from both sites, easy peasy. but I'll show you how to do the full thing today. But I figured I'd start with something fun. I just went to Nebraska this past weekend, late last week through the weekend for the Nebraska astronomers meeting. They asked me to come out and give the plenary. And I showed them OPIS stuff and MWU stuff. And I was thinking, you know, I look at the videos from last year to prep for the ones this year. And last year I was deep in the development of MWU. And in case you don't remember, you're all learning OPIS, of course, but there's this follow-up curriculum, MWU, funded by DoD. That's kind of the next level. And I hope many of you will go on and participate in it and find ways to implement it at your institutions if you're interested. But anyway, last year when I was doing this, I was deep in the development. And so every week I had something I was excited about to show. And I haven't been doing that this time because I'm not developing MWU. I'm doing reports to funding agencies and things that are not fun or exciting to share. But since I went to Nebraska and I was showing off OPIS and MWU, I did a few live demos. And when I was getting ready this morning, the data's still up in Afterglow. So I figured I'd just show you an MWU activity for fun. It'll only take a couple minutes so you can see some of the stuff that happens down the curriculum. And then we'll dive into lab 4. So let me share my screen. What is all this stuff? Okay. Let's see. Let me move this over. Let me move you all over. Spread you out. Okay. Let's see. Okay. So I think like in our first meeting, I talked a little bit about MWU, and it's a follow-up curriculum. It's more advanced technically, although there's actually less math typically. So it's an interesting mix. There's a big focus on imaging, like colored pictures, both in the optical and the radio and archival infrared. So it's multi-wavelength, it's color, which we avoid in OPIS because we're trying to scale to a national level. Things are very carefully prescribed, single exposures, doing a color image, doing a stack for depth, doing radio maps that take a lot of time. So they're not part of OPIS, but the idea is a subset will come back and do MWU in a follow-up course if you decide to offer something like that. And so what I'm going to show you today is one of the radio exercises, because you've been seeing lots of optical things. And there is one radio thing, and soon 2 coming up in OPIS, some spectroscopy. But I'll show you one of the later activities. This is when we're near the end of the MWU sequence, and we're just starting galaxies. And we start with Andromeda being nearby and big. And we do that one totally in the radio. And then we move on to farther away galaxies, and et cetera, et cetera. But the Andromeda activity. So right now, this is our only radio telescope. We're getting ready to integrate more in Australia and the US as part of the DoD grant. So far, this is all we have. 20-meter diameter dish. Again, the largest optical telescopes, excluding the 30 meters under construction, are 10 meters. So this is like twice the diameter of the biggest optical telescope, but it's considered a medium-sized radio telescope. And it's 6 stories tall, 150 tons, and we have thousands of students using it every year through Skynet. And the Skynet 2 system will be even better at dealing with the radio telescopes. We really jimmied this thing into an optical scheduling system. But anyway, key takeaway: it's like a telescope, but with it's like an optical telescope, but with a 1-pixel camera. So if you want to make an image, you have to do something like, these are slides from my Nebraska talk. Something like this. You raster, you move it around, and you collect the data as it's moving. It's called on-the-fly mapping. And we've developed some sophisticated algorithms for filling in the gaps and removing backgrounds and removing radio frequency interference, which is the radio world's equivalent of bright skies. It's, stray communication signals from civilization that are becoming worse and worse, making radio harder. And so we have all this stuff. It's like a 50-page paper in AppJ, and pretty proud of this algorithm. I think it's the best single dish mapping algorithm out there in the radio, which is kind of goofy because if you want to make a picture in the radio, you normally use an interferometer. And so we're the best at something nobody does. But anyway, it's coded in there. We actually have it in the Skynet 1 system now, and so MW students have been using it. I'll skip over all the glories of it. It does other things other than imaging. It does spectroscopy. You just point and collect a spectrum. And so here's a spectrum of Andromeda. And Andromeda is about 3 or 4 degrees across. And the beam of the telescope is 3/4 of a degree. The longer you go in wavelength, the blurrier things get due to the diffraction limit of the telescope. This is something we teach in introductory astronomy with optical telescopes. Of course, atmospheric blurring is even worse, but if you're up in space, the longer the wavelength you go, the blurrier the image. And radio is very long wavelengths. You know, the optical, you're talking hundreds of nanometers. Here, we're talking 21 centimeters. So these images will be blurry, and that's something you accept in the radio, that the images are blurry. They're not going to be gorgeous, but they can be cool, as hopefully this will demonstrate. Anyway, this is a spectrum of the center of Andromeda. So we're not even getting the wings. And in the radio at 21 centimeters, there's an emission line. Cold, neutral hydrogen spits out 21 centimeter emission line. And you see it here. This is Andromeda's. This is the Milky Way. Come to that in a second. But here's Andromeda's, and it's been spread out because Andromeda's rotating. And we're not even getting the ends, right? 3 or 4 degree galaxy. We're only sampling the middle 3/4 of a degree. Well, that's the core. We're getting some sensitivity in the ends. So there's even more emission out here towards the blue and towards the red than this spectrum would indicate. Now, what this is right here, this is Milky Way cold hydrogen, because we have to look through the Milky Way to see Andromeda. And with Andromeda, we're seeing a good chunk of the galaxy and the rotation, so there's Doppler broadening. In the Milky Way, you can have all sorts of different Doppler shifts as well, but we're just looking through a single line of sight, just puncturing a hole out towards Andromeda. And just in that spot, it's a particular redshift. And so you get a very narrow line there. Now, the cool thing in radio is it samples a spectrum. Every time you read a data point, it gives you a full spectrum, whether you wanted it or not. Now, spectroscopy in the optical can be really tricky. In the radio, it just happens automatically. So after we map Andromeda, we actually have a full spectrum at every point in that map. And so after the fact, we can break it into bands. I can take just this part right here, these frequencies, that's going to be my blue band. And just these frequencies, and this will be my green band, and just these frequencies, and they'll be my red band. Remember, the broadening is because Andromeda is spinning. And so if this works out, we make a color image, you can see Andromeda's rotation in color. That's the idea. And we'll also sum all 3 of those together, something we call a luminance band. We teach them astrophotography, and luminance bands are good for boosting your signal to noise. And then we do a narrow band around this, the Milky Way hydrogen. And often when you're doing an astrophoto in the optical, you'll use narrow band for like H alpha, O3, S2, hot ionized gas, and tells you all sorts of things physically. And we'll do the same thing here, a narrow band from Milky Way hydrogen. And I'll spare you the details of how you process the maps, but I'll just pop over to Afterglow where I have them already loaded up. This is I'll come back to that. So here I have the radio maps. I have them grouped together. And so this is the luminance filter. This is all the light of Andromeda. And you can see the elongation. It's about 4 degrees, 3 or 4 degrees across, mostly edge-on spiral. Here's the blue band, which is one side, the green band from the middle, and the red band from the other side. So you kind of see where this is going. And here's the Milky Way hydrogen. So by doing these different spectral bands, we can separate out these physical components because of Doppler shift. And the Milky Way hydrogen's just all over the place, right? Because we're looking through the Milky Way to see this off in the background. And they've learned all sorts of astrophotography stuff. So let's impose this. Let's make the red band. We'll go to the red band here. Let's make it red. Go to the green band. Let's make it green. Go to the blue band. Let's make it blue. The luminance band, the way a luminance layer works is it's meant to be higher signal to noise. So you take your intensity from the luminance filter and your color from anything beneath it in the list. And so for this, I'm going to change the color just to grayscale, but I'm going to change the blend mode to luminosity, indicating this is a luminance band. All my intensity will come from this image, but the color will come from the combination beneath it. And then for the H alpha band, we color it whatever we want. We'll color it bomber. Like in the optical, there's H alpha. We'll color it the H alpha color, or the bomber sequence color. And put them all together, and that's what you got. Now you could do fine adjustments with brightness and contrast and bring out different components and things. I don't know. I get excited when I see this. You're looking through that pinkish, purplish Milky Way hydrogen, seeing Andromeda in the background. You can see it spinning in color. And the point of MW is to use color in all sorts of ways. Optical, radio. Here we're using it to give us Doppler motion. There are other things we can do where, like in the optical, color gives us temperature of a star. In the radio, we can make color images, and the color gives us the emission mechanism, the spectral index, essentially.
Hey,
But anyway.
Dan, if I could ask a maybe
Please.
big question, but you said this corresponds to the rotation of Andromeda. Is it then safe to assume that the red end is red shifted moving away and the blue end is blue shifted moving towards?
Yep.
Is that
The
how that
blue end
works?
is
Okay,
spinning
cool.
towards you, the red end spinning away. And so they then do calculations. They have the velocity, they have the size. So if you know the radius of the galaxy and the velocity it's spinning at that radius, you can calculate mass. We do this in our Milky Way OPIS lab with the rotation curve in lab 7. So you'll encounter that. So they weigh Andromeda. It's not just a picture where they can see it spin, they can weigh it. The central wavelength is blue shifted. Andromeda is coming towards us about 300 kilometers per second, so they can measure the approach. We tell them there's no sideways motion. That's been determined through other means, and so they can calculate an approximate collision time scale. So fun little things that you can, fun little calculations that go with the astrophotography. Anyway, I figured I'd just share an MW activity with you so you can see some stuff that's down the line. The OPIS labs are a little bit more cookbooky. These are a little bit more open-ended, more inquiry-based. So it's kind of next level stuff. But it's orthogonal. Instead of cosmic distance ladder, it's star formation and evolution and galaxy evolution and things like that. This one here, I'm not going to show you today. I'll save it for when we do lab 6 because it's a shorter lab. We'll have a little bit of time. This is an earlier MW activity. They learned how to make pictures like this from their red, green, blue. This is just a red, green, blue combination. It's a stack, but it's actually not too hard to go from the types of images that you're collecting in OPIS to something like this. And then using Afterglow, we extract the brightness of every star. There's like 1,600 stars. We do it in B, V, R, and I. So that's a lot of stars. It is 70, is that right? 1,600 times 4, so 7,400 stars, something like that. Hope I did that right. But anyway, Afterglow makes it easy that it only takes like a minute to process all these images, get all that photometry out, and then we pipe it into one of these extra tools that we made that allows them to plot HR diagrams. And when it feeds in, it cross-correlates with Gaia, so you can get proper motions and distances and throw out the unrelated stars. You can find the cluster. It's like grouping in proper motion space and get rid of everything else. You have nice, clean HR diagrams like the ones in your textbook. We all teach HR diagrams when we teach stars. The HR diagrams in our textbook are completely different from the HR diagrams in published papers. And this tool lets you very easily bridge that gap. And then they can fit isochrone models, age, metallicity, dust. When they measure the dust, they actually come back their image. We have dust extinction curves coded into Afterglow, and you can subtract out the dust, making things bluer to their intrinsic color. Anyway, I'll show you that one in 2 weeks. I don't know. Hopefully that's exciting stuff. Yeah, I find it exciting.
Dan?
Yeah.
I have a bit of a question on this. I'm trying to decide. I want to do maybe 1 or 2 of the MWU labs this semester.
Yeah.
And I'm wondering if you have a suggestion for which one would be good if you had to choose one.
If you had to choose one, I would probably do the HR diagram lab. We have 2 versions of it, a shorter one that I wrote, kind of assuming they've learned some skills through other earlier MW investigations. And then there's one that Daryl wrote that assumes that you haven't done anything yet. It's your first experience. It's a little bit longer, Daryl Jansen. And they have some videos and things. And this tool is pretty well developed and advanced. The module is pretty advanced at this point. Yeah, I would look at that, and it's not deep into the astrophotography yet, so it's pretty easy to do red, green, blue combinations. Yeah, that's a good starting point.
Is there a link you could provide for that?
Yeah, do me a favor, email me, and okay. I'll round up the materials and send it to you.
Okay, thank you.
Okay, let's get back to Lab 4. We started it just barely last time. So let's set it up here. Okay, so what did we do last time? We pointed out we have the usual overview videos. There are a bunch of how-to videos as well, embedded lower in the lab and also listed on the YouTube site. Our video, our meeting from last time, I forgot to post it. I just posted it this morning. So if you were looking for that, it's there now. We also went to the observing guide and realized we needed to put in observations for Lab 5. It's also instructor putting in an observation, this time getting 50 images of an R-Lyrae star for the next lab, which is standard candles. We're into the cosmic distance ladder now. So cosmic distance ladder starts with parallax, and then we go to standard candles, and then Hubble's law. Essentially, that's the short version of it that we do here. But it captures all the key elements. Now, so last time we talked about how to put in the observation for Lab 5, and then we ran out of time because we started with grading. And then you got me all riled up, and I went on a rant about how I'm tired of us teaching seasons and phases. And I've had, like, in the MWU groups, we've had like 3 meetings where this came up in a row just since then. And by the end, I was just digging down deep to the bottom of my soul, trying to find the energy to just repeat the rant for a 3rd time. But anyway, I'm not going to go there this week. Lab 4, here we go. What are the goals? Well, this is parallax. So 4 parts, and you can skip the first part if you want to, though I think it's pretty cool. We start by doing a manual parallax measurement. We take them out of the classroom to a location that you would have to find on your campus, hopefully close to the classroom so you don't lose a lot of time in transit. It basically has to consist of a very straight wall, and across from the wall you have 2 objects, one closer, one farther away. I'll come back and show you the one we use at Chapel Hill and how to do it. But using these things, if you do the globe version of Lab 2, we use the protractors and the strings, get to use it again. This becomes their angle measuring device, and they physically, themselves manually measure the distance to, for us, it's a smokestack on a building across the way and a water tower farther away. Kind of like surveying. But I think it really drives home the concept of parallax and how to measure it. And then we do the astronomical ones. We do the main belt asteroid, which normally you would have collected by now. And if you haven't gotten this far in the sequence, and if Tololo comes back next week, you can still collect the data for real. But otherwise, I'll show you some samples you can use. From there, after we get the parallax, this is Earth baseline parallax, because remember in lab 2, we measured the diameter of Earth. So now we get to bootstrap that, measure distances in the solar system. We start with the main belt asteroid with data that you collected as a class. And then we do it again to Venus. That's the third point here. To determine the AU, how many kilometers in one astronomical unit. That's archival data for reasons that will become apparent when I get to it. Ethically questionable reasons, and you can judge me as you see fit. And that will define how many kilometers in an AU. So then we can do stellar parallax, and that's the last point here, where we do Alpha Centauri, also with archival data for the same reasons. The last three, the first one's its own unique experience. They're doing it manually. The last three, it's being done with Afterglow. It's pretty much the same thing 3 times in a row. Each one has a twist to it, but it's repetitive, but I maintain it's the good kind of repetitive, reinforcing. And if you do the manual measurement and then the astronomical ones, it can be a little bit lengthy. I'm fortunate, the place that I do my manual measurements right on the roof of the building the students are already in, so it does not take long. Even so, the students usually only get through 2 of the 3 astronomical measurements, but because of the repetitive nature, they then know what to do for the third one. They can do it at home. But if you have to walk them some distance across campus to find this ideal location, you may want to split this up over 2 lab experiences, or you may want to cut something out, like the manual component. Equipment, for the manual component, the protractor and the string, a tape measure, because they're going to have to measure the distance between their 2 measurements, and for the rest, computer and internet. Okay, 2 background sections. The first one sets up the cosmic distance ladder. So it's not germane just to this lab, but to the coming labs. In fact, in this chart here, you can see it's connecting the size of Earth measurement in lab 2, some Earth baseline and stellar parallax in lab 4, our Lyrae Cepheids and type 1As in lab 5. Then we do a few little side labs, and we get to Hubble's Law in lab 8. And in the new lab 9, which I haven't written yet, but I will be writing this semester. It won't be ready this semester, but I'll be writing it this semester. They'll measure Hubble's constant. Anyway, the rest of the lab sequence is really built around the cosmic distance ladder, with a few side labs that I think are important. So anyway, I start with this statement here. Distance is one of the most difficult things to measure in astronomy. You cannot see distance. It's one of my favorite phrases. You cannot see distance. And here's an example. The textbook we use has these weird disembodied heads. And I can't use textbook images for copyright reasons, so we hire a company that remakes them, so we're legal, but they use the same disembodied head. So I don't know, I find it kind of strange. So here we have a disembodied head looking out at the stars, sees stars A and B, and he sees them as the same brightness. But that does not mean they're at the same distance, because they can have different luminosities. I know you know these things, but I'm just presenting as you might to your students. So this is just an example of how we cannot see distance. There's more to it. And so we, over the years, have developed a bag of tricks that we call the CDL, the Cosmic Distance Ladder. And each trick works over a certain range, and hopefully it gets us out to some objects that we can use for the next trick. We calibrate those next objects with the ones we've already done. It gets us out farther. We calibrate a new trick, gets us out farther. And that is one of the subtle things here. Particularly, we'll see it in the next lab a lot. Calibration, the bootstrap process. Each technique calibrates the next. And of course, calibration is one of the trickiest concepts for students to wrap their mind around, even though it's one of the most critical things that we need. Okay, I explained that figure. I point out here, I think I say it in words. either here or in the next section, but we can see it in the chart here. Earth baseline parallax, using the best techniques possible, gets us out to about 500 AU. Stellar parallax using Gaia gets us out to about 10 kiloparsecs, kind of the beyond the center of the galaxy. Okay. Now, the other background section is specifically on parallax. And, I started with the standard finger experiment. I'm sure you've all done this. Here's my canned joke. Feel free to use it. I say, okay, everyone, grab a finger, preferably your own. And then I have them move it close to their face and close one eye and notice what they're covering up on the background wall, and switch the other eye. Notice what I guess I should be here. Notice what a big shift that is. And then I say, okay, put your, again, the camera here, extend your arm all the way out and do the same thing. And they notice it's a smaller shift. And I say, cut your hand off and move it farther away. And of course, that's a joke. And then it's a smaller shift. So the idea is, if you know the distance between your observing points, in this case, your two eyeballs, and you can measure that angular shift using a little bit of math, you can calculate the distance from your eyes to your finger. That's the idea. And surveyors do this just with more sophisticated equipment. And so the distance between the observing points is called the baseline. And then you got the angular shift. Now, astronomically, we have these two types that we do: Earth baseline parallax and stellar parallax, which is Earth orbit baseline parallax. So here's Earth baseline parallax. This figure is actually for the moon. The moon is close enough that if you observe it simultaneously from opposite sides of the planet, where the orientation, the baseline, is perpendicular to the line of sight to the moon will shift 4 moons, 3.8 moons. It's a remarkable effect. If you take these two pictures simultaneously and compare them, the moon really moves. Of course, you seldom have background stars when you image the moon, so you wouldn't notice it. But anyway, it's a big shift for the moon. You get farther out, it will be less, as we just said. Your main belt asteroid should only be a couple arc seconds, if I recall correctly.
You just grab them.
Right.
Okay.
Nope.
And here is stellar parallax. Once we know, here, I'm gonna mute Anna. Okay. Once we know how many kilometers are in AU, we can now move up to stellar parallax. And so here we're taking not simultaneous images, but images 6 months apart, where the baseline is 2 astronomical units always, because that's the diameter of Earth's orbit. But it's the same deal. You compare these two images, the close by star will appear to shift compared to the far away stars. And if you know the baseline, you measure the angular shift, you can calculate the distance to the star. And here are the two figures. And these figures should look familiar. We used the same geometry in Lab 2 for size of Earth, and Lab 3 to figure out the physical. We measured the semi-major axis of a moon going around a planet in arc seconds, and we converted that to AU. So we used the same geometry. We're using it here. We'll use it again in Lab 6, where we measure the physical size of a spiral nebula, as they were called back then, but a galaxy. There is one tweak the educators previously have asked. They want me to, this figure is confusing. I should have put the arrowhead not there, but here. Like this one starts, this is the angular shift. It goes from here to here. This one goes completely around. But by drawing it here and putting the label here, it makes it look like this little angle's 360 and could cause confusion. So I'll move the arrowhead and the label up there by spring semester. But this is Earth baseline parallax, looking at something nearby. This is stellar parallax, looking at something nearby. But it's the same. It's a ratio. The angular shift as a fraction of this whole circle, 360 degrees, is equal to the baseline divided by the circumference of this big circle, centered on the object. You can see it here. And you can see it here. And the circumference of the big circle is 2 pi times the radius, and the radius is the distance between us and the object we're trying to get the distance to. So you can replace circumference with 2 pi distance, solve for distance. It's just the baseline, either Earth's diameter or Earth's orbit divided by 2 pi, times 360 divided by the angular shift, where they have to remember to convert it to degrees. When they do their manual exercise with the protractor, it's in degrees. And I probably mentioned this in lab 2. You don't want to get any old protractor. There's one that comes with the hole pre-drilled at the 0, 0 spot. That makes life much easier. And so if you're looking for these, and you can't find them, email me. I'll send you the Amazon link. But you can get like a box of a lot for cheap. Okay. Yep. Okay. So we're ready to go into the procedure sections. And we'll start with the manual exercise. And so this is a picture of my setup. And once you find your setup, if you decide to do this, once you find your setup, you'll want to make an equivalent picture. This is up on the roof of the building my students do their lab in. So I create a piece of paper. It has this on it so they know what to look for. And it has the things they need to measure. One angle, another angle, and the distance between their two observing points. They're going to stand on one side of the deck, make an angular measurement, stand on the other side, make an angular measurement. The difference between those is the angular shift, and they need to measure the distance between them, the baseline. So on this, so they don't have to take their laptops with them. I have the sheet of paper. It has the 3 spots for that, times 2, because I have them do 2 objects, a nearby object and a far away object. For me, it's a smokestack on this building that's across the courtyard, and then the water tower that's farther away. And you want to pick 2 objects that are kind of perpendicular to your wall. It keeps the math simple. If it's at some kind of angle, then the math is more complicated than what we do at this level. And the other point is you want to pick a wall that's pretty straight. This is, been poured, it's been laid out, it's a very, very straight line. It's about 100 feet long, it's very straight. It's a nice straight edge that we can line the protractor up against. If your objects are far away, your shifts may only be a degree or something. And so you want to make sure that, they can line up their protractor to similar accuracy. Of course, you can go for a smaller setup and that gives them more freedom, greater accuracy. So here I have my picture, but you'd put your picture on your piece of paper. And I've written the instructions. In many places it says, on-campus students at other institutions, like the true distance to your objects would be provided by your instructor, that kind of thing. So it does work. It doesn't have to be, you don't have to be at Chapel Hill to use these instructions. Even though I have my picture and my numbers here, I've written it such that you can make it work anywhere. So once you find your location, the students go to one side, make the protractor flush against the wall, lower their head so the eyes are flush with the protractor, hold the string out, line it up, and then slowly raise their head and get the measurement. Protractors are good to degree increments, so they can probably measure to 1/2 degree accuracy, maybe a little bit better. So the first angle goes here, second angle goes here. Here's the difference. Then they measure the distance between their observing points. And so we bring up some tape measures. Our tape measures are 25 feet long. We also bring up some yardsticks. And I don't tell the students how to do it. It's kind of fun to watch them figure it out. Some people will take the yardstick and go end over end over end. Some people will take the tape measure, go to full 25 feet, and then shift it until they, mostly their baselines are like 100 feet. So they have to do this a couple times. The smart ones realize that the deck is lined with 2-foot pavers and they just count the pavers. But, you measure the distance. It goes here in feet. And then they use their equation and they calculate the distance. They're doing the nearby object first. And that goes here. And here I say my nearby object is 360 feet. But if you're a different institution, your instructor will tell you, use Google Maps to figure out the true value, basically. And so you'll give that to the student. They input their true value here and calculate percent error. Then they do it again for the more distant object. And this is kind of critical. You want to do more than one object because the farther away you get, the greater the inaccuracy becomes. We'll see some questions about that in a second. And this goes to the point of why this technique fails after a certain distance, and we then have to do other techniques. Discuss sources of error. Yeah, I have 3 points, but I list 6 of them. So just quickly, difficulty positioning the string. Now, technically, if they got it wrong in the exact same way for both of their measurements, it wouldn't be a source of error. But I don't expect that from them. If they say anything about difficulty positioning the string, okay, that counts. Difficulty holding the protractor flush against the wall, or maybe the wall wasn't perfectly straight. Precision of the protractor, it only has the 1 degree increment, so that's a limiting factor. Measuring the distance, particularly if they had to go end over end, there's some uncertainty there. It's small uncertainty. They have 2 more that nobody ever gets, but they're here. One is, what if your object's not perfectly perpendicular to your line of sight? Then the equation doesn't quite hold. Also, if your object's too close, I mean, if your object's line of sight is not perfectly perpendicular to the baseline, that's what I meant to say, then the equation doesn't quite hold. And the second one is, if the object's too close, that equation is a small angle approximation. So if you're talking angles 20, 30 degrees, you're going to be building up error. Most people don't figure those out, and that's okay. If they get 3 of the other 4, they're great. And then we have some pointed questions here, or to the point questions. Which of your measurements was less accurate? Which should have been? Either could have been less accurate, but most likely the farther one is less accurate. The farther away it is, the smaller the angular shift, the more difficult that will be to measure. And then that leads into a question for a fixed baseline. At what point does parallax cease to be an accurate technique for measuring distance? And I say, do not say 10 kiloparsecs, because in the background section, I said we could do parallax out to 10 kiloparsecs. So students would just write 10 kiloparsecs. And so we added that bit there. We're looking for something deeper here. The measurement fails when the angular shift becomes smaller than the ability of your angle measuring device to measure angles. That's when parallax fails. And what are 2 ways you can improve the accuracy of your parallax measurement? Get a more precise angle measuring device than a protractor and a string. Ultimately, Gaia is the best. And but surveying equipment would be a step up from this. And the other way is to use a bigger baseline. Okay, so that's the manual part. And I think you can see doing it manually will help drive the concept home, where doing it just on the computer with astronomical data, they may not be fully cognizant of the geometry that's going on. So I do like the manual thing if you can swing it. Okay, questions about that? We've got 18 minutes left. We should be just fine.
I have just a brief question.
Yeah.
I tried to do this last semester, and I had real trouble finding, like you say, you have that perfect space to do this.
Yeah.
I had trouble finding something that was really ideal on our campus. I guess it's probably, you don't have any advice on that, but
well, I do actually, because we also do this with online students, and the instructions are written to work for online students as well. And they will often do it inside on a much smaller scale. Like they'll use a table and put 2 things across the room. So if you can't find a place on campus, you could probably create a setup in the lab. I remember as a grad student, we had a lab like this, and we did the measurements in the room. That works too. And I think in here, there are also instructions. If you don't have a protractor and string, you can actually use the compass app on your phone. It's less accurate, but it's more for the online students who may not have this. But if you do this, you should just order a box of these. The inexpensive. Okay, let's move on to the astronomy, the main belt asteroid, which unfortunately we don't have any data on this semester, but we've already had that discussion. This is how to place the observation. We talked about that before. So now identifying the asteroid, and then we'll measure the distance. So let's see. I'm going to use, well, first I'm going to show you where the CAN data is. So here, if you open file, you go to the sample directory, Astro 101 lab, parallax. I have 3 of them here taken back in 2010, 2012, 2014. Any of them work just fine. You go into them, skip the directory that says movie. We don't do those anymore. That was a previous version of Afterglow. Parallax. It has 2 figures. These were taken really close to simultaneous. One's always from Chile and one's from somewhere up north, usually the Moorhead telescope. And you can just use those and you're good to go. But instead, let me show you how it would normally work with data you collect yourself. So you collected this data. Skynet's a little slow this morning for me. Not sure why. I'll have to email my programmers. Here we go. Okay. And it's been a while, so I'm going to have to use the search feature. My observations, it was Juno last fall. Click again. My mouse is also a little busticated from its recent travels to Nebraska. Got banged around. And I did this right before. Here we go. Yes. Okay, so I made 3 attempts. I used the Promptu telescope in Chile, got 13 of my 15 observations, and I had 2 of them that I tried up north, up in Canada at Saskatoon, and Triple RT, which is in Southern Virginia, not far from me. The Saskatoon one was weathered out, but I got 13 observations from Triple RT as well. Let's take a look at the Chile ones first. And so this was very unusual. I had cloud cover, so much so that I didn't actually get enough background stars to have a WCS solution. And for this to work, you need to have a WCS, except on one image. This here, you see I have enough background stars. Normally, this won't be the case for you, but if you have these little yellow warning signs, it means you did not get a WCS, and you're probably going to have to reshoot. Now, what I would, before reshooting, I'd go through and find my best one and put that in Afterglow. There is a tab on the right in Afterglow where you can update, you can try to put a WCS on it. And the Afterglow WCS tool is better than Skynet's. And so maybe you can add a WCS to it. Normally, this isn't an issue, though. Okay, but I got one here, and it's number 6, and it happened at 5:05:09. Okay, so I'm going back. Skynet, killing me here. Okay, now I'm going to go to the Triple RT, 5:05:09. Looking through. Here's one at 5:05:07 within 2 seconds. It's also number 6. So those are the 2 I want. I want number 6 from each. And so you would tell your students how to find this. And, it's in the group directory under your account with this observation name and this observation. It's 2 separate observations and which exposures they want from each. And they'll load them up in Afterglow. But you got to do that little time matching first because the asteroids move. If you compare 2 from even like a minute apart, the separation that you'll see may not be due to parallax, may be due to motion. Okay, so I'm going to go here to Afterglow, Files, Skynet, User. This will take a second. Well, didn't. I'm going to search on Juno. There they are. So I'm going to go into Prompt 2, Reduced. And let's find number 6. Here it is. Open. While that's coming in, I'm going to come here, come back to User. Search on Juno. Oops, gotta spell it correctly. Triple RT, Reduced. And this was also, just by chance, 6. They must have started at the same time, or well, it could be a variety of scenarios, but this one's a bigger field. It'll take slightly longer to load, but it won't be too bad. And I think I'm coming over here to the little gear. I have sync orientations on. So as I hop back and forth between these two, they've been synced. So you can see the prompt field is smaller, the triple RT field is bigger. Zoom into that prompt field. So one of these is the asteroid. How do we tell which one? Well, for that, we're going to use the DSS, just like we did in Lab 1. They know how to do this. We go to the gear, import DSS. There it is. And I'm going to split it. You can split up, down, or left, right. I'll split right. And I still have that sync orientation on. So I see it already, but it may take the untrained eye a little bit longer. What we have the students do, and it's described in the lab and the videos, is come over here to markers, turn on centroid clicks, and start marking stars that are common between the two images. That star is that star, that star is that star. This is this one. You can see in this case, because the cloud cover we had at Tololo, we did not go deeper than the DSS. Usually we do go deeper than the DSS. And so we'll usually have more stars than the DSS. And you got to be careful not to pick one of those as your asteroid. But usually it's quite apparent. We have this big bright thing that's not in this one. So the students are told to mark some reference stars just to get their bearings, and then to mark the asteroid in their image and label it. And there's the label right there. Frame it up.
Hey, Dan, can you control the size of those labels? I haven't found a way to do that.
Let's see.
I can change the placement.
You can change the placement, but not the size, unless it's under the accessibility features. Under settings, theme styling, default font weight, default font size. I don't know if that will change it in the image. Let's find out. No, it changes it everywhere else. I'm going to go back. This is for people with seeing impairments. We offer these things, but it did not change it here. And I guess when I did that, it erased all my markers and labels, but you get the idea. You would save the snapshots, and then you upload them into, come on, mouse. Why is that not saving? Oh, my browser jammed up. Let me reload it. Busted something, so. Well, it's coming back up. I'll go back to the lab here. And so they load their image, they load the DSS. This is a different field with references and the asteroid mark. Like this is worth 3 points, this is worth 2, 1 point for marking the asteroid, or at least a plausible, well, it has to be the asteroid. That's how they find it. And now to measure the distance to the asteroid, we start with the angular shift. Let's get rid of the DSS. So we have our two images. We have prompt in Chile, and load this one back in. And this is triple RT. Okay. So to measure parallax, it's pretty easy. You go to the aligner tool, and we're going to select those two images, Juno and Juno. And you got to pick one as the reference, though it does not matter which one. One will be aligned to the other. Make sure you're in WCS mode and all these things are on. This may actually be the thing that's not currently in the video. We did some redesign of Afterglow, and so I'll have to update the video to accomplish that. But you see it here, and submit. It should only take an instant. Okay, one is aligned to the other using the WCS solution. That's the world coordinates that comes from the background stars. And then we're going to stack them. We're going to add them together. So I'm going to pick my two now aligned Juno images, aligned to the background stars. if you want to propagate the cropping, that should be on by default. Doesn't matter, but all the stuff can stay the same. We're just going to average the two, no fancy rejection or scaling. Submit, and it'll create a new file. Here it is, Juno stack. So this is a stack of the two. Now to bring it out, you got to go to the display settings, and we're at default setting, but if I keep adding, if I up the saturation, you can see it here. We've already identified this is the asteroid, and we have two images because it was imaged simultaneously from different sides of Earth. That's parallax. And so they measure the distance between it using the plotter tool. If the centroids are, if they're well separated, you could turn centroid clicks and use it here. In this case, it didn't work. Apparently, I saturated this whole region. So I'm going to do it again without centroid clicks. For most of these, you just have to kind of do it by eye, unless you have well-defined centers. And they save this, and that will upload to their lab as well. And the angular shift is right here, 7.2 arc seconds. So there's the uploaded image. Similar scenario. Their angular shift. Then they figure out the baseline between Chile and whichever telescope they used up here up north is what fraction of Earth's diameter. I don't actually have triple RT on here. It's newer. I'll add it, but it's pretty close to Moorhead, which is 55% of Earth's diameter. We did the chords through the sphere for them. And so they write down, okay, the two observatories are 55% of Earth's diameter apart. In lab 2, we measured Earth's diameter. And what did you measure? And what is the true value? Even if you didn't do lab 2, as long as they put something here, they'll get a point. But this is just to remind them that these are building on each other. Oh, you measured this previously. Now we're going to use it. But we then switch over to the true value or the best value so their errors don't accumulate. So the baseline between the two observing points is the fraction of the diameter times the diameter. So that's there. And then you have the baseline, the angular shift. They just have to convert it to degrees, and they get the distance to the main belt asteroid, something times 10 to the 8. We tell them it's typically between that times 10 to the 8 and that times 10 to the 8. Is your measurement reasonable? Discuss sources of error. Most significant sources are how well you're able to centroid the asteroid in each image. Were the images simultaneous? If not, there is also some motion of the asteroid between the two images. And the one that no one gets, and so this is only 2 points, is what, it's quite possible that the baseline was not perfectly perpendicular to the main belt asteroid. Earth's tipped and we're on some chord, and so that will mess things up as well. But we're not trying to get a precision measurement, just kind of in the ballpark. I'm going to go a few minutes over. I do want to wrap lab 4. The rest goes kind of quickly, though. Any questions so far, though? Make sense? Okay. Now we're going to repeat this for Venus. And the reason we're doing this is we want to figure out how many kilometers are in an AU so we can then do stellar parallax. So Venus is its orbital period is 0.62 years. Kepler's third, which they've already done, means its distance from the sun is 0.73 AU. We are 1 AU by definition. So often in lecture, I'll give them the question, parallax to Venus at closest approach. And here's the closest approach. We're 0.27 AU apart, the difference. The parallax, I think, is 1 arc minute. And so they can calculate a distance. It's a nice, simple problem. But you can't do it in reality because you can't observe Venus in this position because the sun's right there. So although it's good in lecture, in lab, we have to be a little bit more sophisticated. We have to do it some other place in the orbit. So we're going to give them archival data when Venus is in this phase, which means it's right here. That's the only place you have that phase. And we provide them the information. That's 1.34 AU away when this archival data was taken. Okay. Now here's the tricky thing. To do Venus, you need to see Venus without saturating, but you also need background stars to align to. And Venus is so bright that if you image long enough to see the background stars, you've totally blown out Venus. And so you can't do the measurement. If you image briefly enough that you have Venus, you don't have any background stars to align to. So we tell the students that I spent the big bucks and got these custom filters made that are neutral density in the middle, blocking most of the light in the middle, but not in the outskirts. So we can have our cake and eat it too. In reality, I wasn't going to spend this would probably be a $3,000 or $4,000 filter, and I need 2 of them for simultaneous imaging. So this data is doctored. And I don't tell my students it's doctored, but I leave that up to you. The way you could tell is it's 8-bit and astronomical images are 16-bit, but no one's ever figured it out. Okay. So let's do that measurement. It goes real quick now that you've seen how it's done. We're going to go to, these are in the sample directory. That's why they don't collect it themselves, right? It has to be the special central neutral density filter to do this. Astro 101 Lab, Parallax, Venus. Gonna load them both. There's Venus Moorhead. Here's Venus Prompt. I still have the sync orientations on. That's why the one is shifted, but you can see it's lined up nicely. And so again, we're going to align. Let's clear out Juno. We're going to select Venus, Venus. Select one as the reference, doesn't matter which one. Submit. They're aligned, so now we're going to stack them. Clear out Juno, select Venus, Venus, stack. And here's the Venus stack. And see all the stars are aligned, but there you see the parallactic shift to Venus. So you use the measuring tool. Can't centrate on this because it's a big mess. You have to eyeball the center of one to the center of the other. About 7 arc seconds. Back to the lab. They put their angular shift. Again, using the same table from above, what's the fraction of Earth's diameter from Moorhead to CTIO? It's 0.55. And so they calculate, multiply by the true diameter of Earth, get a baseline. Baseline and angular shifts gives a distance to Venus in kilometers. And this distance is 1.34 AU. So divide by 1.34 and you have the number of kilometers in an AU. We give them the true value, 1.5 times 10 to the 8. They calculate percent error, sources of error, same as before. Difficulty selecting center of Venus in both images. Could be contaminated by the motion of Venus through space if they were not imaged simultaneously. May not be perfectly perpendicular. But now they know how many kilometers are in an AU. So the last activity is Alpha Centauri. Same deal. It's so bright that we have to use our special, very expensive central neutral density filters that I sprung for. This one's actually kind of, it's kind of funny. I got my postdoc, Aaron Lacluse, to make these for me. Clues is the most ethical person on the planet. Like if we were in Chapel Hill late at night observing and we go out to get a bite and the streets are dead empty, he will stand at the cross light until the walk symbol comes on before crossing the street. I'm shocked that he didn't downright refuse to make these images for me. Anyway, he did a good job. You can see the diffraction spikes and everything. Let me show you this one because there's one little subtlety. So open, back to the sample directory. Let's see, 101, Parallax, Alpha Centauri. Oh, the other cool thing about this is the way you can tell the background stars are not correct. In the old Skynet, if someone forgot to type in the right ascension declination, it imaged 0, 0 in the sky. And I have so many images of 0, 0 that when we made this image, we put Alpha Centauri on our 0, 0 image just as an internal joke, but no one's ever noticed. Anyway, I got the 2 images in here. Now these are taken, they're doctored, but if they were taken 6 months apart. This is stellar parallax. There's the January observation. Here's the July observation, both taken same scope. But you do the same thing as before. Oh, you see the 2 points there, 2 stars, Alpha Centauri A and B. And this is what leads to confusion. Students will measure the distance between them instead of the parallax of either of them. So let's go to the aligner, clear out Venus, Alpha Centauri, pick a reference, submit. And then the stacker, clear out Venus, Alpha Centauri, now that they're aligned, submit. Where is this image? Oh, there it is here. Since they started with different, it uses the name as much as in common, but since the first character differed, it just blank dot fits, but here it is. Zoom in here, and the mistake the students made, as I said, is they'll measure the distance from here to here. But if you go to brightness and contrast, come on, mouse. This is Alpha Centauri A. It got kind of saturated. It's not going to be good for measurement. But here's Alpha Centauri B. You don't want the distance between A and B. You want to know how much either of them shifted. And so I zoom into B, and the lab tells them to do so. Again, it's too close, so you have to kind of eyeball it. Angular shift of 1.8 arc seconds. So in the lab, there's the image they upload, their angular shift. What's the baseline in AU? It's 2 AU. It always is for stellar parallax. We have them put this in kilometers. We could do this in AU, but I really want to emphasize how each step is bootstrapping on the next. So we say, how many kilometers did you find in an AU? Okay. How many kilometers are actually in an AU? Let's use the actual value, calculate the distance to Alpha Centauri in kilometers. It's here. Google the true value in kilometers, percent error, and the sources of error, difficulty center, selecting the centers, and they may not be perpendicular. The simultaneous is not a problem anymore because these are on purpose 6 months apart, right? So you can't say, well, maybe they weren't taken simultaneously like you could with Earth baseline. Anyway, that's the lab. I sped up at the end because I was running out of time. Thanks for waiting. Any questions about this or anything? Because I'm here until my TA show up. Okay, no questions. I think it's a little bit long. That's the only problem. With the manual exercise, it's a little bit long. But the manual exercise really gives them a feel for what parallax is that they may not get from looking at the astronomical images without seeing the triangle. You know, they don't see it physically. They're just seeing the results of imaging from different positions. But the astronomical part, I do like the repetition. Repetition can be good or bad. I think this is good repetition, reinforcing, and each one adds something new in the solar system, and then calibrating the AU, and then getting to the next star out. And then we'll continue with standard candles farther and farther next time. All right. Thanks, everyone. I'll let you go.
Thanks, Dan. Yeah, I had one question for you, just in general. Have you ever considered, some of these labs are you know, quite a mouthful.
Yeah.
And not that the content is bad, I'm not implying that, but especially, you know, especially lab 1, but like this lab, have you considered breaking these into like multiple labs, even though they're, that, you know, because I mean, it's like a little more bite-sized, less intimidating for students. And, you know, it just seems like they get a better sense of accomplishment. I kind of feel like that's one of the challenges on lab 1, is it seems like there's so much stuff that if you could maybe do something simpler, like maybe even the first lab, just get some images that you could do like on the right away, and then, you know, it sort of gives them a win, right?
Yeah, although they're all, you know, the whole thing's packaged in a single lab, you're certainly welcome to spread it out.
Are we able to do that? Because I noticed with the edit is like turned off.
Yeah, you're not able to do it. You're able to spread it out in time. You can spread it out in Yeah, I do see the point that you're making. It'd be nice for them to do a chunk and then receive a grade for that chunk, and then do another chunk and receive a grade. Well,
Well,
you
it
can
also
do,
integrate better with the LMS, right? Instead of
yeah,
like you doing it all manually, I'm not saying that the flow is
no, I get
necessarily
you.
poor as much as like chunking. I guess chunking is the word for it, right?
Yeah, chunking.
Kind of chunking them into more assignments, like one spreads over 2 weeks. And I understand there's also because you have to take images and wait for them, but at the same time, like, I don't know,
You could chunk that second week in 2 chunks. And for lab 1, for this, you can break it into like the manual chunk and the astronomical chunk. I'll talk with Cengage about this. Once we get past the MWU development, I'm planning to go back to Cengage and say, look, we're now serving 1.5% of all astro survey students in the country. You really need to move us up to one of your sponsored products, and then we'll get additional attention from them. The problem is the editing. It's not even easy for me. They don't give me editing capability. That edit
really?
button, yeah, that edit button is just changing the number of points things are worth.
So I'm sorry, I didn't understand that. Cengage, I'm just starting to engage with them actually on another class. So they basically are doing the work, or basically
For this product, you can build your own products, but this one is sufficiently complicated that the arrangement, like the accordion stuff, is non-standard, as I understand it. And so we have a revision feedback cycle, and it can be very slow and painful.
So I wasn't aware you were like in a revision feedback cycle with them. Obviously, that is like it is with any book, or like it is with a textbook. That's a little more complex than just saying, "Oh, just change this,"
Yeah. So what some people have done, not many, but some people have gone off the Cengage system and built their own versions. A lot of work went into building it and making all the auto grading work and years of debugging. So it's not necessarily something I recommend. Also, as I do updates, you don't have that. And so if you go off on your own, it's 2 things. You can go off on your own, make your own versions of these, but then you have to buy the telescope time separately.
Sure.
Yep. And then
and not necessarily saying, "Oh, this sucks, got to change." I just think that again, I'm coming at it. The good news is I'm coming at it for the first time. So I always like to share feedback when someone's coming out the first time.
I appreciate
Like, and I did hear Tom talking to you the other day about some students getting turned off, and I wonder if part of that isn't because lab 1 is such a mouthful, like swallowing an elephant.
Yeah. I hear you.
And it's just, and I realize there's a whole process associated with this. It just would be, and it would be probably easier for people to adopt if it was chunked up, because that's nice because it integrates well with your LMS, right?
I think when I go back and have these discussions, try to get the product elevated, chunking is something that we could seriously consider at that point. Right now in the feedback revision cycle, I'm just happy if they make my updates within half a year of me sending them.
Right. Yeah, of course. Right.
Right. But once we become a sponsored product, which is my goal, because my goal really is for this to become a national curriculum, and I think we could go it alone, but going through one of these things, like one of these mega companies like Cengage, is probably the way to do it. Because once we're a sponsored product, all of their reps will be in every university pushing this thing.
I mean, there's a lot of infrastructure that these type systems give you. So, teaching programming as well. We use some of these. Well, we went away from these type systems. Now we're headed back to them. So, there's a rationale here that makes sense.
One thing I'll ask for is, can I actually be given control to edit my own labs and get out of this feedback cycle? With MWU, I'm not going this course. We're building our own things in Pressbook sites, and we may sell the time over WebAssign until we have our own product set up.
Oh, really? So you kind of roll your own?
Yeah, with MW, we're going to
I asked because I'll be using that next fall.
yeah. I mean, right now it's just in Google Docs. It's going to take me teaching it 3 times before I feel that the product is ready, like all the way ready. And lots
Sure.
of people are using it now anyway, and with, you know, all the good and bad that comes with using an early version. But
Well, I'd
this
love to teach it in the fall because it's going to be just our astronomy concentration, and there'll probably only be like 5 to 7 students
the spring
next
or
fall.
next
So,
fall. That'd be even better. By then I'll have it all in Pressbook. I should have videos. It should be much farther along.
But the fact that it's only 5 to 7 students, that even if it's a little rougher, still has rough points, you know, I'll be able to work individually with the students a lot more. So
Yeah. And, you know, we've had a lot of discussions, particularly over the past week. OPIS training is one thing, and we could do it in Zoom meetings, once a week as we are, and it seems to work. MW is trickier. There's a lot more to it. It really is next level. And a person like you're going to have no problem. You're going to understand it and do it. But
right, I got a pretty strong background in imaging.
Yeah.
So
but some instructors struggle to learn OPIS, and MW will be an even bigger struggle. And we may actually have to go with a different professional development model where, we meet for a week in the summer at Green Bank and have in-person, long day, but fun.
yeah, just do it. Like a workshop type thing or a deep intensive
Yeah, we may
immersion
have to,
session.
maybe in combination with Zoom meetings.
It'd be great to have an excuse to go to Green Bank again.
Oh yeah. I go 2 or 3 times a year. I find lots of excuses. I take my students there to do programming excursions, like my undergrads, because there's no time during the semester for undergrads to actually do anything, just dribs and drabs. But fall break, winter break, spring break, I try to take them for 2 of those. Usually, they want to go. I wouldn't steal their breaks if they didn't want to, but they want to go. And it's a 24/7 crazy experience.
I was gonna say, are you still doing the one in the summer? I know you were doing the one.
Yeah.
Would you do the one in the summer with that's like the radio-orama? That's like pretty much, like no sleep till Brooklyn kind of thing.
Yep. And then I take my undergrads back for these little programming trips, and they were all recruited out of that program, so they know the experience, and they love it, and they get like a month's worth of work done in like 4 or 5 days.
Yeah,
because they're all together. There are no distractions. We can answer each other's questions. We run 14-hour days.
Well, that experiential learning is important. It's one thing I like about Coastal is we're actually trying to do more and more experiential learning like that, and trying, because we realize that students tend to just do much better in those kind of environments, right?
Mm-hmm. It seems, from our previous discussions, you and your institution are very proactive about this stuff.
That's one thing I really like about it. I was kind of surprised, that they're trying to be pretty proactive, and we're trying to pull more astronomy that way. So I see your TAs are coming in. So
Okay.
I was just going to ask you about the chunking, and just if you'd had considered that, just from a standpoint of trying to optimize the flow a little bit, right?
Yeah. At Chapel Hill, we have our labs completely separate from our lectures. They may not even be the same topics. And so they're hour, 50-minute labs, and it works out. The current division works out fairly well, but these are Chapel Hill students. They're usually fairly exceptional. And I know at other institutions, they would appreciate chunking.
Well, yeah, especially because like when we're merging it in, we have it's just sometimes
you're mixing it with lecture as well.
Yeah, and so like
really help there. Yeah,
it just seems like it's a little less intimidating.
Yeah.
For students, right? I notice a lot of students, we still have that imposter syndrome, right?
Yeah.
think they can't do it, although
I still have it.
Though I had somebody get 105 on the first lap, so
Oh, great,
she did a great job.
great.
All right, well, I'm going to let you you go off and work with your team. Thanks, Dan. Appreciate it. We'll see you next week.
Okay, my pleasure. All right, I'm gonna stop the share and I'm gonna stop the record.